Section number 5 of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. This is a LibriVox recording. All LibriVox recordings are in the public domain. To learn more or to volunteer, please visit LibriVox.org. Recording by Blaine Aidan McCoy, Riverside, California, March 2019. Nuclear fission. New elements. In 1934, Enrico Fermi began his first experiments involving the bombardment of uranium with neutrons, experiments that were to change the face of the world. Fermi had found that slow neutrons, which had very little energy, were easily absorbed by atomic nuclei, more easily than fast neutrons were absorbed, and certainly more easily than charged particles were. Often what happened was that the neutron was simply absorbed by the nucleus. Since the neutron has a mass number of 1 and an atomic number of 0, because it is uncharged, a nucleus that absorbs a neutron remains an isotope of the same element, but increases its mass number. For instance, suppose that neutrons are used to bombard hydrogen-1, which then captures one of the neutrons. From a single proton, it will become a proton plus a neutron. From hydrogen-1, it will become hydrogen-2. A new nucleus formed in this way will be at a higher energy, and that energy is emitted in the form of a gamma ray. Sometimes the more massive isotope that is formed through neutron absorption is stable, as hydrogen-2 is. Sometimes it is not, but is radioactive instead. Because it has added a neutron, it has too many neutrons for stability. The best way of adjusting the matter is to emit a beta particle, electron. This converts one of the neutrons into a proton. The mass number stays the same, but the atomic number increases by 1. The element rhodium, for example, which has an atomic number of 45, has only one stable isotope, with a mass number of 103. If rhodium-103, 45 protons, 58 neutrons, absorbs a neutron, it becomes rhodium-104, 45 protons, 59 neutrons, which is not stable. Rhodium-104 emits a beta particle, changing a neutron to a proton so that the nuclear combination becomes 46 protons and 58 neutrons. This is palladium-104, which is stable. As another example, indium-115, 49 protons, 66 neutrons, absorbs a neutron and becomes indium-116. 49 protons, 67 neutrons, which gives off a beta particle and becomes tin-116, 50 protons, 66 neutrons, which is stable. There are over 100 isotopes that will absorb neutrons and end by becoming an isotope of an element 1 higher in the atomic number scale. Fermi observed a number of these cases. Having done so, he was bound to ask what would happen if uranium were bombarded with neutrons. Would its isotopes also be raised in atomic number, in this case from 92 to 93? If that were so, it would be very exciting, for uranium had the highest atomic number in the entire scale. Nobody had ever discovered any sample of element number 93. But perhaps it could be formed in the laboratory. In 1934, therefore, Fermi bombarded uranium with neutrons in the hope of obtaining atoms of element 93. Neutrons were absorbed, and whatever was formed did give off beta particles, so element 93 should be there. However, 4 different kinds of beta particles, different in their energy content, were given off, and the matter grew very confusing. Fermi could not definitely identify the presence of atoms of element 93, and neither could anyone else for several years. Other things turned up, however, which were even more significant. Before going on to these other things, however, it should be mentioned that undoubtedly element 93 was formed, even though Fermi couldn't clearly demonstrate the fact. In 1939, the American physicists Edwin Madison Macmillan, born 1907, and Philip Haug Abelson, born 1913, after bombarding uranium atoms with slow neutrons, were able to identify element 93. Since uranium had originally been named for the planet Uranus, the new element, beyond uranium, was eventually named for the planet Neptune, which lay beyond Uranus. Element 93 is therefore called Neptunium. What happened was exactly what was expected. Uranium-238, 92 protons, 146 neutrons, added a neutron to become uranium-239, 92 protons, 147 neutrons, which emitted a beta particle to become Neptunium-239, 93 protons, 146 neutrons. In fact, Neptunium-239 also emitted a beta particle, so it ought to become an isotope of an element even higher in the atomic number scale. This one, element 94, was named plutonium after Pluto, the planet beyond Neptune. The isotope plutonium-239, formed from Neptunium-239, was only feebly radioactive, however, and it was not clearly identified until 1941. The actual discovery of the element plutonium came a year before, however, when Neptunium-238 was formed. It emitted a beta particle and became plutonium-238, an isotope that was radioactive enough to be easily detected and identified by Glenn Theodore Seaborg, born 1912, and his co-workers,